Yes, class. Am I audible to all of you?
Yes, ma'am.
All right. So in the last class yesterday, we had completed dual nature. Dual nature was done. So what is left now? Now we have to do atoms today. So see, atoms is a small lesson, but just few points are present that you have to keep in mind. So again, the same thing. Theory part will be covered here only, and few numericals we'll have that will be we'll be able to we'll be able to complete it. So atoms, this is a small lesson. Just pay attention to it. See, firstly comes the Bohr's quantization equation. So this equation is L is equal to mvr. That means angular momentum. This is integral multiple of h by 2. Now, when we say integral multiple, this means n is equal to 1, 2, 3, 4 like this. So L is equal to mvr means nh by 2 pi. Now, few postulates you have to remember. And class, this formula is important. This formula can be asked to you. And apart from this, numericals can also be there on the basis of this formula. Now, yes, first postulate says that. First postulate is a very easy postulate. This says that the massive central core portion present is known as the nucleus, and the electrons keep on revolving. This is the basic structure of atom. So basic structure of atom, all of you already know about this. So this is exactly what is the nuclear concept. So first postulate highlights about the nuclear concept. Second is again quantum condition, the same quantum condition which we have just now discussed, that angular momentum. That angular momentum is integral multiple of h by 2 pi. See, linear momentum's formula. What is the formula of linear momentum?
MV.
MV, right. So for angular momentum, one more component gets multiplied, that is the perpendicular separation, that is MVR. So L becomes equal to MVR, which is equal to NH by 2 pi. So this is the second condition. Third says that all these orbits which are present, they're not radiating any amount of energy. They are stationary present. It's the electrons which are moving. Electrons are jumping from higher level to lower level to higher level. Orbits aren't moving. Orbits are fixed with their specific diameter radius. And these are the electrons which keep on revolving, and as well as they change their orbits also. All right. So this is the third postulate regarding it. Then comes the frequency condition. See, frequency condition is nothing new. E is equal to h nu. Yesterday only we had seen. Same thing. E is equal to h nu here only. It's just that frequency condition means that, see, when we say that electrons are jumping, when we are saying that electrons are jumping, electrons are moving from one particular orbit to another particular orbit like this. So when we mean that, what is exactly meant by this? See, there are different layers of orbits. So if electron jumps from lower to higher level or higher to lower level, any of these, frequency is emitted, energy is emitted. So associated with the energy, you'll be having wavelength, you'll be having the frequency. So associated energy is there, and energy's formula is h nu. So it's like higher minus lower's energy. So this formula is used also a lot. E is equal to h nu. So E2 is the energy of, let's say, the second shell. E1 is the energy of the first shell. It is jumping from second to first. So what will be the energy difference? E2 minus E1. And now E2 minus E1, you will get some net energy that you can equate to h nu. This is what is known as frequency condition. So this is nothing new. You just have to remember that when electrons are jumping, they are emitting or absorbing radiation. They'll absorb radiation and move up. When the electrons are going up, that is from a lower level of orbit, they are moving up to a higher level of orbit. In that case, it absorb energy and then move. And when the electrons are actually moving from higher level to a lower level, electrons are descending down, then the electrons emit radiation. Now you can use h nu, hc by lambda, whatever things you have studied yesterday, everything is applied over here. These are the four major postulates which you have to remember. Now, Bohr's theory of hydrogen atom. See, Bohr's theory of hydrogen atom. Among this, you have to remember the formulas, just the formulas. So first formula is the formula for velocity. This formula derivation, I think you can remember, because remembering of it is directly not possible. So what you can do, just remember this. Equate electrostatic force with the centripetal force. Centripetal force means electrons is revolving around the nucleus, no? So some electrostatic force is providing the necessary centripetal force. So it means mathematically we can say that electric field is actually equal to the centripetal force. So centripetal force formula is mv square by r, and electric field's formula is, we know, kq1 q2 divided by r square. So one electronic charge is E, second one is ZE, means proton times the electronic charge by R square. So when you equate this, you get the value of R also, you get the value of V also, because directly learning velocities and radius formula is a little difficult task. So you can perform derivation, that will take a lot of time. Or if you can remember the formula directly, then well and good, you can remember that directly as well. So the radius formula, yes, one more thing. This formula also of radius is used a lot, where radius is 0.53 into n square by z times angstrom. So this is an angstrom. Remember, if you are asked in meters or in nanometers, you want to change the units, then directly put in the values of it. All right, change 0.53 into nanometers, picometers, whatever is needed by you. Right now we are calculating angstrom. All right, so R is 0.53 n square by z angstrom. This much is the amount of radius. Now see, depending upon the number of orbit, if I say electron is only in the first orbit, if I say electron is only in the first orbit, so n will be 1. If I say electron is on its second orbit, so it means n will be 2. So you will not put 2. It becomes n square, that is 4. Do one thing, note down few points, the important formula. No need to, I think, write the derivation, or if you want, you can quickly write this. Fe is equal to Fc. Just write these main formulas till here. Class, this one thing also you can note it down: kinetic energy, total energy, and this is potential energy. So kinetic energy is directly kZe square by 2r. Total energy is just negative of it, and potential energy is kZe. Just write down these three as well. Regarding the Rydberg's formula and the spectral series. So do not write the spectral series, no need to write it and draw it. Just remember Rydberg's formula, you will be able to manage it. Just remember the sequence, Lyman series, Baumol series, and all. So angular wave number, this is given by Rydberg's constant multiplied by 1 by n1 square minus 1 by n2 square. So n1 and n2 are what? The shell in which the electron was initially present, and N2 is the electron shell in which electron has come. So initial and final number of shell. And Rydberg's constant, just remember this value. See, 1.0973, you don't even need to remember, because usually your answer gets solved if you use 10 to the power 7. So 1.0973 into 10 to the power 7 per meter. This is actually the value of Rydberg's constant. Just remember these series in this form. Just remember it like this. See, from anywhere electrons can come, but they should land up to the first orbit. If they land up to the first orbit, that means it is the Lyman series, and Lyman series have their wavelengths in the ultraviolet region of the electromagnetic spectrum. EM waves, all of you are aware of, so that this is ultraviolet. And if electrons from anywhere they are coming to the second orbit, then it is the Baumol series, and the wavelength of electrons that will lie in the spectrum of visible region. Then anywhere electron from 0, infinity, anywhere electrons can come from the 6th shell, 7th shell, 100th shell, infinite, and land up to the third one. So that gives us Paschen series. And for Paschen series and rest of the series, the wavelength lies in the infrared region. Next is the bracket series. So again, in the final value of electron, this should be 4. Likewise for fund, this is 5. So just remember the sequence and keep on putting it in the formula. Now what you have to remember is first excited state and second excited state. That can be confusing. See, first ground state, when we say ground state means n is equal to 1. That is clear. N is equal to 1 means ground state. N is equal to 2 is the second state, right? We call n is equal to 2 as the first excited state. So all your excited states begin from second one, second, third, fourth, fifth. So first excited state, second excited state. So if I give you any number, One lesser than that would be the excited state of it. For example, if I give you fourth excited state, so it means fifth orbit I'm talking. That's why excited state is one lesser than the number. Likewise, so ground state means the basic one, infinity basic one means the first one, first orbit. Infinite is there, and in between you have excited states. This you should remember regarding from this series. And apart from this value of energy, at least till this fifth one you should remember. First value, energy is formula. See, energy's value, this is minus 13.6 divided by n square electron volt. Electron volt, you can convert it into joules also, because you already know value of E, electronic charge. You can put it in, get it. Here, class, till E5, E1, E2, E3, E4, E5, this is used a lot, all these values. The rest of this you need to calculate, but at least till fifth one, E1, E2, E3, E4, you'll be using it a lot in the equation. So it's better, instead of every time calculating it 2, 3, 4, 5, you directly remember the values. So E1, E2, E3, E4, and E5, you should remember till here. E1 is obviously very easy, minus 13.6 itself. E2 becomes minus 3.4 electron volt. E3 becomes 1.51 electron volt. E4 becomes minus 0.85 electron volt. E5 is minus 0.54 electron volt. This much you should remember for energy. This much energy is sufficient. Limitations are there. Limitations you don't need to do. These you need to do. See, when Rutherford's experiment and all the experiments were conducted, just go through all these experiments also which were conducted. Now see, nucleus is present. So it was observed when the whole experiment was concluded, it was observed that some of the particles got deflected, right? 3 observations were made. No, some got deflected, some moved, or some just rebounded back to 180 degrees. Some showed very slight deflection, all these. So out of one was, some electrons went and they exactly bounced back, making one angle of 180 degrees. That means what? Something massive is present, which is repelling it. That was just showing that protons, and means this was just showing that nucleus this is having a positive particle in it. So at a certain distance, before even reaching the nucleus, suppose this is the nucleus, this is the alpha particle. Alpha particle, before even colliding with it, at a certain distance, at suppose this much distance, alpha particle turns away. At this much distance, alpha particle turns away. So when the alpha particle is turning away, this means what? Here in this case, this means this is a positive number that is given, right? Positive amount of quantity is present in the nucleus. That was just determining the sign. Now we know, but earlier this was an experiment. So that separation which is left is known as distance of closest approach. Suppose this is the nucleus, this is the distance by which alpha particle is getting separated. So this much of separation which is obtained, this is called distance of closest approach. So for distance of closest approach, you have to remember this formula here. Class, this one. 2k Ze square by kinetic energy. Above k that is written is 9 into 10 to the power 9, dielectric constant, which you study in electrostatics. And the second one, kinetic energy. The K, this Ke that is written below is kinetic energy. One more thing, some alpha particles also got deflected. They didn't pass through it, they got deflected. So that angle of deflection by which they crossed it, that is known as impact parameter. So impact parameter, not that distance, that angle is known as deflection, but the distance that is observed. For example, they are turning away. So there is this perpendicular distance which is existing. That perpendicular distance is known as impact parameter. So impact parameters have formula. Again, K is there, 9 into 10 to the power 9, Ze square cot theta by 2 divided by kinetic energy. That's it. This is what you should remember. Quickly write these two and write the energies value and Rydberg's constant. That's it. No need to draw the Lyman series and all. All right, quickly note this part. Then we'll jump on to the numericals. Just give me a minute, class. These questions are from semiconductors. Just a second. Class, see, this says that when an alpha particle of mass m moving with velocity v bombards on a heavy nucleus charge Ze, its distance of closest approach. Now see, formula of closest approach. If I'll write kinetic energy here, half mv square. This is actually equal to 2 I'll write it in the denominator. So this is equal to qze square divided by 4 pi epsilon naught r naught. So from here you can directly see r naught and m, they are inversely proportional to each other. So this is D option. Just note it down quickly. So third question says that in Rutherford scattering experiment, what will be impact parameter if B is 0? So see, impact parameter is 0, angle we have to find out, deflection we have to find out. So this also we have discussed. Yes, Marika, right answer. So this is 4 pi epsilon naught ZE square cot theta divided by 2. This is the kinetic energy that is present. This term is entire term is equal to 0. So everything else will also be equal to 0. Only cot theta by 2 will be equal to 0. So theta by 2 will be 90 degrees. So theta will become 180 degrees. So this is again the option. Note it down. Yes, B option. See, this is the formula for energy, nth orbital minus 13.6 by n square electron. This is, I think we have also written it right now only. But if it is not hydrogen, then Z square you have to multiply, whatever is the number, atomic number. But we all know Z is 1 for hydrogen, that's why. The ratio of wavelengths of the last line of Balmer series and the last line of Lyman series is. So we'll use the Rydberg's constant here, 1 by lambda. This is Rydberg's constant. Z square, no, we write. Z square 1 by n1 square minus 1 by n2 square. This is the general formula for Rydberg's constant. Alia, C option, no? Or D option you're saying? C option. Please write the option. Otherwise, it becomes confusing with whether you are talking about the option number or the content. Yes, yes, yes. Correct. C option is the right answer. C. Now, see, for both of it, for Balmer series and Lyman series, for Balmer series, this is going to be Z square R. Now, we have seen Lyman was the first, second was the Balmer. So this is going to be 2 square and minus infinity square. Whenever this says no last line, anywhere, last line means n2 is equal to infinite. And when it says shortest wavelength means the next consecutive one. So this is 1 and 1 by lambda for Lymer. This is going to be Z square R. 1 by, this is the first one Lymer. So 1 square minus 1 by infinity whole square. So this becomes C. If you take this is equal to Z square R by 4. And this is just Z square R. Just take their ratio. So lambda, Balmer is asked no first. So Balmer by wavelength of this. So again, this will get reversed. This will become 4 Z square by R. This is going to be Z square R, Z square R, Z square R. Cancels. The ratio becomes equal to 4. So yes, Alia was correct. C option. Quickly noted down, class.